So let's talk about exponential growth and decay. So this is the equation we've been using a lot. This here is our starting point. Maybe we start off with 10 bacteria. This would be like time is equal to 0. This over here would be our ending value. So we've got 1,000 bacteria when we're all done. This is how long. And decay is our growth or decay factor, constant. So that adjusts how fast things grow or decay. Again, that was the continuous equation. If it's something that's done periodically, like when we're paying monthly bills or getting interest quarterly, this is the equation we would want to use here. Again, that's our starting point at time equals 0. This is the ending value. N would be, for example, 12 if it's monthly. There's time, just like in the equation above. And K, a lot of times, K could also be R, or we might use an I. And again, that's how fast things are growing or decaying. Another form of this would look like y sub 0. Then we might have some letter b raised to the power of kt. So I'll give you some examples of that equation. It's very similar to this, but instead of using e, we're going to use some other number. And then the last one you haven't seen before, this is the logistics equation. And again, it's the continuous form. You see you've got the little e right there. Time, just like before. Here's our growth and decay factor. A is the final, it's the final value. And then I'll show you how to find the B in a little bit. So let's try to look at some graphs. A simple graph of growth looks like this. And a simple graph of decay looks like that. Now, if you don't have the equation, though, how can you tell them apart? So let's start off here. We have y equals y sub 0 e to the kt. And again, I mentioned another way we might write this would be y sub 0 times some letter b raised to the kt. So let's talk about how you can tell if it's growth or decay. So if b is greater than 1, we're going to have growth. An example of that might look like y equals, and actually here, let me stick a number in. Let's say we start off with 3 bacteria, and they're doubling really fast. So my b is 2 in this case, raised to 0.7 t. So my b is greater than 1, so we're going to be growing. If I have the exact same thing, but I have a negative 2 in here, if b is less than 1, excuse me, I don't want to be negative here. So 0.7, so it's less than 1, then this would be decay. Let's try another one here. If we start with 3 bacteria, I'm doubling, but this time I'm going to make my k negative. So I have negative 0.7 t. So here I have k is less than 0. So this was going to be decay. Where up here we had a positive k, and so it was growth. Now the question would be, what if I have a negative k and I have a number that's less than that? So in fact, let's write this out. This is kind of an unusual situation, but if I have 3 bacteria, 0.7 raised to the power of negative 0.7 t, this actually is going to be, turns it back into growth. So I have two criteria here that would make you think decay, but when you have both at the same time, we go back to growth. Now let's talk about the logistics equation. So here's the graph. And what's happening here is kind of interesting. You can imagine we start off with some bacteria in a pond or something in a petri dish, and they grow and grow and grow, but then they start to run out of food, and there's only so much food around it. So it actually flattens off to some steady level. And that was the A in the equation I showed you a little bit ago. That's going to be, the bacteria will just kind of hang out there at that level. They can't grow any faster than that because there's not enough food. So in a little bit, I'll show you how to calculate the K and the B in that equation. So let's do some exponential equations here. So here's the example. We start off with 6 bacteria, and after 15 minutes, we have 150. So let's just use the equation we had up on the board here. Y equals y sub 0 times e to the k t. Now the reason I picked E is with the bacteria, they're kind of growing constantly. It's not like every day I step in and boom, the bacteria grow. I could have used the other equation if that's the way the bacteria are growing. But I use the continuous equation because that's really matches better how the bacteria are growing. So we know that we started off with 6 bacteria. We don't know the value for K, but we do know that T is 15 minutes. And we do know that after 15 minutes, we had 150 bacteria. So now what we should be able to do is just solve for the K. So let's divide by the 6. So now we have e to the raised to the power of 15k, and 150 divided by 6. Now, to get the k by itself, this is a good spot to take the log, but it's going to be easier for us if we take the natural log. Both will work because that allows us then to bring our exponent in front. So over here I have the natural log of 25. Over here I have 15k times the natural log of e. But the natural log of e is just 1. So now we have that the natural log of 25 is equal to 15 times k. I can divide by the 15, and I find out that my k is equal to 0.2146. Of course, we expected a positive k because the bacteria are growing. So next question, how many bacteria after 30 minutes? So this becomes pretty easy. All we have to do, y sub 0 again was 6 bacteria, that's what we started with, times e raised to the power, but now we know the k. Right, there's our k. E raised to the power of 0.2146 times t, and in this case t is 30 minutes. So you can plug that pretty much directly into your calculator. You might want to watch, you might need an extra set of little parentheses right there. And we pop out with 3,750 bacteria. Next question, how about how long until we get to 1,000 bacteria? So take the same equation, but now our final results is going to be 1,000. Actually, let me write it over here. So we're going to start off with, we have 1,000